First of all, we try to finish the time and frequency today. And for your reference, your homework, I gave you homework Tuesday night. I'm sorry, today talk also. You can see there's actually like almost 10 homework, so I think it's too short for 1 week. So the deadline for the homework is next Thursday instead of Tuesday. And they will cover the discrete time Fourier transform and part of time and frequency. And another announcement I would like to talk at the end of the lecture, but anybody has access, anybody don't have access to the MATLAB? You don't have access? Okay, so let's talk after the class. So next homework, which probably given next Tuesday, which is doing in the MATLAB, today we will finish time and frequency. And we have finished Fourier series, continuous and discrete time Fourier transform, and time and frequency. So it's enough, it's time to do the Fourier transform using other software. So I will show you, at the end of the lecture, I will show you briefly show you an example how to use the Fourier transform MATLAB. And of course, I will provide a material so you can follow in your MATLAB. And then I will assign you homework maybe depending on the lecture, maybe next Tuesday or next Thursday, so then you can practice some Fourier transform in the MATLAB instead of handwriting and compare with your handwriting result. So let's start for today's lecture. So in previous lecture, we talked about that time and frequency. We have one tool, Fourier transform, bridge the time and frequency. And we talk about that two concepts. Basically, one is group delay. When the system is linear, the phase is linear, we have learned that the system or signal can be jeopardized by changing the phase. So by changing the phase, the signal or even input and output of the system can be totally different from original signal. So now the phase is very important. And we pick up a special case that when phase is linear, case A and B in your textbook. From A to B, even though there is some delay, however, the basic function, basic shape does not change. So what you can see from here is when there is a kind of linear in frequency, when phase is linear in frequency, then they will be delayed. However, the shape does not distort it. That's what you can see here. From this idea, we introduce a concept of group delay. Group delay means we basically do the derivation by frequency and put minus to compensate the minus slope. So this is basically the minus slope of the phase. So if this slope is constant, that means the delay is constant. So we expect a constant delay. And also we introduced a second concept. We introduced the body plot. Of course, everyone knows it. I think. However, what I can say now here is we try to plot a signal, dividing them to magnitude and phase, because as I explained in the board, if you know the amplitude, if you know the phase, you can calculate what is complex number. Therefore, all the plot show them individually. However, if you combine the information together, you can reconstruct what is the original signal. That's what you can see from this lecture. Also, body plot is quite useful in case of continuous Fourier transform. However, in case of discrete one, there are not so advantageous compared to continuous one, because they are repeating. Remember, discrete time Fourier transform is repeating in frequency, periodic in frequency, and continuous in frequency. So they are repeating basically, as you can see here, repeating by period of 2 pi. So it does not have much meaning, but we can plot it though. And from this thing, how we can utilize this body plot? One way you can utilize is design the filter. Design of the filter is more, you can learn about it more in digital signal processing class, which probably open, I'm not sure if I open it. However, it will open it in other like electronics engineering or IT engineering, those department opens digital signal processing. So what they do there is, you may hear similar things. Okay, when you do transfer to the frequency and change the time period, they will change the amplitude in frequency. They will change the period in frequency. Those kinds of things. And based on things, you will design several filters. Because let's start with the basic one, which is in this lecture is not about the filter. So the reason I cover this chapter is because I will give you a little bit taste how to analyze a filter. Because a filter is used in everywhere. So when you talk about the filter, what we have learned is either high-pass filter or low-pass filter. As you can imagine, high-pass filter means, is it recording? High-pass filter means they pass the high frequency signals. That's what they mean. Low pass filter, they pass low frequency signal. That means in case of high pass filter, block low frequency signals. In case of low pass filter, they block high frequency signal. So let's talk about some filter now. When we talk about the system, we have learned about Fourier transform, we have learned about the system, we have learned about linear time invariant system. So let's think about the system. Let's say this is our system, has a transfer function h, j, omega. Okay, and assume that we have an input which is xt, corresponding Fourier transform of x, j, omega. That's what they say. We have output yt, which has corresponding Fourier transform y, j, omega. What is their relationship in y, h, and x? What is their relationship in Fourier transform? Circle? Yeah, right. So we basically multiply them together in frequency. Of course, in time, we do the convolution. We learn about the Fourier transform. Now you can change the Fourier transform and just multiply them together to find the output. So by this meaning, let's think about in frequency domain. Let's think about them in frequency domain. Let's say x, this is frequency domain. We never drawn in this way before, I think. In frequency domain, x, j omega, say they have frequency like this. For example, they have like this. Let's assume it. You can draw it other ways. You can draw like this. If you are a very offensive person, you can draw like this. If you are a very calm person, you can draw like that. Whatever you want to do, just draw it. whatever input you want to draw it. And we want to see what output looks like. Let's do some tricks. If the system response, we have talked about system response for a long time. We should say HT, HJ omega, H, EJ omega, system response many times. Why we are doing it? Because this is one of the ways we are utilizing it. Say, we already know what is the frequency response of Fourier transform. Say, if you happen to have your system is flat in frequency. If your system is flat in frequency, let's just talk about amplitude now. If it is flat in frequency, what will be the output? What will be the output? Well, keep in mind, I think you already know what it is, but let's rephrase what we have learned. This is the input having amplitude a little bit change. Looks like ear of a cat, I think, but they change by frequency. Assume that we have a system that is flat. Then what will be the output? Because as you can see in this equation, output is multiplication of h and x. So if you remember the convolution, convolution is also what? Shift in time and multiply together and add them together. This is simpler than that. Just multiply this by this. So let's draw them together. In convolution, we reverse it, move, and multiply. In this one, it's simply multiplication. So we just multiply this by this. So this point multiplied by this point is multiplied by this point multiplied by this point multiplied by this corresponding frequency. So as this is flat, the shape will come as it is. So they will come like this. Assume that. Right? So if you have one, output will be same. If we have two, if we have two over here, output will be, so if this is 1, there will be 2. If this is 4, there will be 8. So there will be maybe a little bit exaggerated, like this, maybe. However, the basic shape will not change much, right? Basic idea that, okay, it looks like an ear of the cat, this still hold. What about if the system response is low pass filter? Low pass filter is what? Let's have a more strict meaning. Low pass filter is what? Low pass filter is passing low frequency component. So they block, they do not pass high frequency component. What's the meaning of it? So say that this is low pass filter actually. So let's use it in here. So they're over here. Say that this is 1. From here until this frequency, 0, low frequency relative to this higher frequency component, they pass because they are this one multiplied by 1. So they will come in output, they will come as it is until this frequency. However, when the frequency is higher than certain threshold, then they will be multiplied by 0. Something multiplied by 0 is 0, right? So that means output is 0, ideally. So they will come like this in frequency, not in time. So what you can see now, there is a lot of different frequency component is entering the system. However, the system, because of the system response, we keep on talking about system response for many times. Because whatever input looks like, system response decides what to show as an output. The output, if this low pass, that means they only pass low frequency component, relatively low frequency component. They block high frequency component. Likewise, if you have high pass filter, if you happen to have high pass filter like this. From 0 to this frequency, there will be 0. So from 0 to here, there will be 0. And from here to higher frequency, they will looks like this, right? So if you see this yellow one, which is using the high pass filter, that means they do not pass the low frequency component, block low frequency component, and pass the high frequency component. That's what we are talking here. So those high pass filter and low pass filter you have already learned from circuit majorly. But interestingly speaking, in case of mechanical system, when you learn about the mechanical system, I think I mentioned about this in the beginning of lecture. When you talk about the mass stamping, you probably remember that this will be given as force mx double dot plus kx. I'm sorry, there's nothing like this, right? When you plot it, when you do the Fourier transform, they were given by s squared. Actually, this is Laplace transform. They were given like this, and there will be f in frequency. And the input what is input to the system? Force or displacement? Which is input to the system? One of them, force. Displacement. I don't know. Force, right? Because input, think about it this way. Input to the system means we stimulate, we activate the system. So we have to pull it or shake it, give a force to activate the system, right? So say that Ft is our input to the system, there's our system, and the output is X. Because as we activate the system, there will be displacement is generated. So how we do it? Input to the system is Xs. Output of the system, in reverse way. Input to the system is F. Output of the system is X. And we were given by like this, right? And when you increase this one, you can say special case like this. And if you increase the frequency, then this one goes down, right? When you increase this frequency over here, the value increase as the denominator increase, the total value goes down. Is it right? So if you increase the frequency, if you go this way, then the amplitude goes down. So expect low pass filter. I'm talking about mechatronics now. So this is basic of mechatronics. Because circuit and mechanical system has very, very, very similar properties. Maybe only one difference is, if you remember the circuit, they were given by S plus something over 1. This one is S squared, right? So what you can expect, when you increase the frequency, how fast they decrease. This one is square, this one is not square. So if you increase the frequency twice, this one decreased by roughly by 4 times. This one decreased by only 2 times, right? So the slope, if you say this one, the slope is like this, then the slope for this one will be sharper because they drop faster, right? Because this one is called second order filter. This one is order over 1, the first of the filter. This one is second order filter, right? So basically, mechanical system, electrical system has very, very, very similar because they stem from same physics. However, one major, they can make low pass, they can make high pass. However, in case of mechanical system, it's very difficult to make a high pass. Also, the drop ratio, I would say drop ratio, there's different meaning. However, the speed of dropping is faster in mechanical system. That's maybe the only difference. Other than that, they're quite similar. Let's go back to here. So before we move to other type of filter, let's talk about this one a little bit more. When you, this one, is it okay to erase this one? 네. 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 So 그게 뭐냐? So what he asked is in here it will be j omega square, right? And j omega square m plus k will be minus omega square m plus k, right? So when you increase the frequency, there goes down, right? That's what you're talking about. Actually, you can think in two ways. So what he says is, if you say this S, special case of S is j omega in Fourier transform, when you do that, there will be minus over here. Going minus over here. So that means if you increase the frequency, this one goes down, goes smaller because k minus something. That's your question, right? So actually, you have to think about the phase because the way I'm talking now here is only the amplitude. We are not talking about phase yet. You can think in this way. You can think that this j omega come as, so too small for here, 6. So if you say like this, then you can change it to minus like this, roughly say. And what is the amplitude of this one? It can be, if you say amplitude, they're always positive, right? So you can think them either way, like the minus plus or plus minus, if you take minus as a phase. So that's how we do it. Because we use this shape because this cannot be minus, right? If you keep on increase, they go to minus amplitude, which doesn't make sense. So we put minus as out, we take a minus outside and make this one plus and make this one minus, right? In this way, this is how it goes. So let's go back to here. Before we talk about the next page, it's easier to see this. So what is the meaning of passing high frequency? What is the meaning of passing low frequency? Let's think about that. So in case of this, let's begin with this one. In case of X, how we can analyze X? So we have learned Fourier series, Fourier transform. So yes, use it. In Fourier transform are continuous in frequency, right? Fourier series is picking a point of Fourier transform. Do you remember that? So let's think about that using this X graph. This is their Fourier transform. Assume that, of course this is not. However, assume that this one has Fourier series. That means we are picking up points from this graph, right? This is the amplitude of this are corresponding, those amplitude are corresponding AK. That's what, actually there's T over here. We talked about that before. If you think about this yellow, what is the meaning of it? Say that the first one is A1, second one is A2, third one is A3. So what's the meaning of it? That means the frequency over here, omega 1, the signal will be, one signal has amplitude of A1, frequency of omega 1. Second signal, amplitude of A2, frequency of omega 2. Third signal, which is higher frequency, amplitude of A3, omega 3. They are added together. That's how we see in time domain. It's a time domain, right? If you say starting from this point, how we develop from here to Fourier transform, we make the spacing to be infinitely small to get the Fourier transform. So to see those lines, what you can do now here is, okay, there, of course this is wrong, There is a little bit faster than this, but a little bit slower than this. There's another frequency exists. There's infinite number of frequencies exist. Infinite number of frequency having different frequencies, slightly slower than this, slightly faster than this, slightly slower than this exist at this point. We add them together to see the signal of X. So also you can think that X has a frequency or those sine waves having all of the frequency shown in here, having different amplitude. So once again, this is wrong explanation. This is not true. That's not mathematically true. This because Fourier series only exists in periodic signal. This line has frequency everywhere. So maybe periodic, maybe not periodic, typically not periodic. So this is wrong because this one does not exist in Fourier series. But let's start from Fourier series first. Fourier series, we can analyze that there is several frequency components having different amplitude, and we add them together to reconstruct the original signal in time. Let's extend the concept a little bit. Let's extend our concept a little bit. So in Fourier series, we have multiple frequency components, add them together. That's the thing. Let's say we have more frequency component, slightly slow, faster than this, slightly slower than this, as infinite number of frequency. Because there is an infinite number of frequencies between them, and add them all together. That will be the time domain signal of this X. That's what we can conceptually think about from frequency to time. So this one, if you draw it like this, white, you can think that, okay, this is a signal has many frequencies. It may be frequency in from here to here. They have component in every frequency that you can think in time domain. When you have a high pass filter over here, that means among these many frequency components, they do not from this component to this component. So from here to here, they pass through the system. From here to here, they cannot pass the system, right? That's what you can see from here. So what's the meaning of this graph in frequency domain? That means let's do the similar analogy what you have done before. So say that we initially X has the frequency component in everywhere, right? Now, this one cannot pass. This one can pass. That means this system decides which one to pass, which one does not pass. So among those many signal, summation of those many different frequencies, those many signals having different frequency, only signals having frequency higher than certain value, they pass. That's the meaning of a high pass filter, right? So that means, let's simplify the problem. Say this is omega, the lowest one over here. Let's say this is this. Second one is 1, 2, 3, and 4. First one is relatively slow. This is 1, 2, 3, 4. This is high frequency faster, low frequency lower. So 1, 2 does not pass, 3, 4 pass. So how will the output will be looks like? There will be only fastly moving component left at the output. So relationship from here is high pass filter pass high frequency component. The meaning is they only passed, so high pass means in frequency domain, what we talk in frequency domain. In time domain, what you can think is they pass fastly moving component only. Slowly moving component, it does not pass. That's how we design, how we conceptually think about the system over here. Before we move on, any questions? So let me introduce other filter. Let me introduce other filter. So we have learned high pass and low pass. What about band pass? Band pass you often see from the lecture, I think. So high pass pass high, low pass pass low frequency component. Band pass is they pass a band. So what's the meaning of band? Certain group kind of things. So what this one says here is they looks like this. So not low, not high, somewhere between them. So they assume that, okay, we are passing from omega 1 to omega 2, and then we block it. So if you have something like this, then they pass, they are 0 over here, they come like this. So you can totally change how things looks like. Of course, there is another thing, say notch filter. Notch filter. Notch is what? Notch typically say if you have a block, if you have a brick, then notch means they have a slightly looks like this. That's a notch. So notch is we try to reject certain frequency. So they looks like if they pass everything, only block, only does not pass a certain frequency component. That's notch filter. So it looks like similar. So when notch filter happens, then they only pass certain, they pass everything, but do not pass certain frequency component. That's notch filter. So this and this one maybe looks similar, but slightly different function. This one tried to pass certain frequency component. This tried to reject certain frequency component. There's a major difference. How we can use it? How we can use it? So let me stop a little bit. People can follow. Okay, so how we can use it? For example, if you, so let me redraw this one a little bit. If you have a system or input you measured, and this is output of your system, happen to be output of your system, and output looks like this. First of all, you may interested, you want to see this more. You are more interested on this one more. Then you select band pass filter, which is shown in here, to pass like that, and this is your filter, and they will pass like this, right? So if you want to look at this, then you can do that using band pass filter. If you don't like it, this looks very unstable, you don't like it, then you use a notch filter. You use a notch filter, so they reject this one. So the output will be looks like right. So of course there's another bandpass filter. They pass multiple of it. That's possible. How we do it? Use a cascade of system. So say you have one system has this frequency, the other system has this frequency. If you cascade them, what happens? So remember about this. So what I'm saying now is the frequency over here are from here. So this first one has system like this, second one has system like that. If you pass them cascade, what will be the what will be the total system response looks like if you cascade them? When cascade, you have to multiply, right? How the output looks like, right? Because this and this one has any overlapping, so the output will be 0. So this is wrong configuration. If you make them parallel, and add them together at the output, what will be their frequency response looks like? Then there will be this and this, right? So what I'm saying now here is the filter don't have to be one. You can cascade or you can parallel what filters. There's one example that we talk about parallel system, we talk about cascade system at the beginning of the lecture. That's how we can utilize it. So those are all kinds of different filters. You can design the filter, utilize as a component. You can cascade, you can parallel, or you can use a bandpass, you can use notch, you can use a high pass, you can low pass, depending on signal you want to take a look at it. That's the reason filter is very, very popular used in many systems. Even in a computer, they use a filter inside. If you many of the noise, they are either flat in frequency or high in low signal. However, most of the signal we want to take a look at is low frequency, because can you move 10 times in a second? Can you oscillate like 10 times in a second? Of course, if you see the movie, somebody can do it. But 10 times in a second is what? 1,000 hertz, 1K. So if you want to measure the human body, you don't need 1,000 hertz, because you never can make 1,000 hertz. So other than 1,000 hertz, either harmonics or noise. So if you make a filter higher than 1,000, block it, that means those signals higher than 1,000 is not we want to have. So you can use it like that. So let's think about how you can do this. The ideal filter, they assume a perfectively selected, meaning that they sharp going like this. They are sharp. We can separate on 1 and 0 sharply. But as you can imagine, so we talked about that before, it is not. So before we move on, let's think about how the signal will look like. If this is frequency component, this is frequency. Now we talk about the time. As this one is low pass filter, the one shown in the screen is low pass filter. They did not pass high frequency component. They only pass low frequency component. So assume that we have a step response. Step response is, what is step? Step is what? In time, step is, this is step, right? Sum of delta function. Sum of delta function, that's a step, like a unit function. That's what we talk about. I think you learn about this in the engineering mathematics when you are a freshman. Actually, sophomore. Say that this is input to your system. What will be corresponding output? This is step response. Output when input is step. So that actually looks like this. Of course, what we learn from engineering mathematics, they would say, okay, come like this, goes like this, and think about what's the delay. I think you already calculate, okay, those tau equals 1 divided by RC. Memorize it, just calculate, right? So let's think about that a little bit. So if you say RC, I think some of you taking the power electronics from me are familiar with this. R does not have delay. Because if you remember those delay, input and output should not respond simultaneously. Output, say output is a current, this is input. When input is given, there is no time-related component. So input and output is same time. Capacitor or inductor. Voltage is so differentiation or integration, they require time domain signal, time domain information, right? So that means we need some memory, we need some delay, we expect some delay. In case of the thing you have learned, when you probably learned that they were given like this, and this is from 0.10% to 90%. There is a delay. They proportional to the 1 over tau. Tau is given by RC or 1 over IC. This one you have learned before. So you have a C over there because there is C like this means there's a delay. Because you only have R. This one always comes as RC, not just R. If you have R, there's no delay. If you have C or L, there's delay. So we are calculating those delays. This is what you have learned before. So let's think about that a little bit more detail. Actually, they are not looks like this. They are not looks like this. In reality, they looks like this. So say that if you have step response, they come on the observing, they do like this. First of all, they are not going to 1. They have some kind of overshoot higher than the stable value. Those one, the highest one is called overshoot. Where do you can see it? Where do you can see it? Well, let's look at it. So the first one is overshoot, and then they oscillate until they go to the stable point. So you can see two kind of things. First one is overshoot, which is the maximum value they go higher than the desired value. Second one is oscillation behavior, sometimes often called ringing. Say that they still waving until they go to stable condition. So if you remember electronic circuit class, they talk about the settle time. The time they go to, the time required that those ringing is more than say 1% or 10%. Those are settle time, right? So this is, you first learn about how fast they can go to the value you want to have, and then how fast, how long you have to wait until they settle down. So you have to learn about those two information. This is the same thing. Overshoot means how fast, or kind of how fast they can go to the first value. Typically, those value higher than desired value happens the first step. So it's one called overshoot. And then they will ringing. And those ringing amplitude is given by the second one. So if you think about the step, there will be either overshoot and ocean barrier always happens. One of the way you can decrease this one is what? The way we can decrease is what? So let's go back to here. How do we decrease the overshoot? How do we decrease the oscillation? Have you ever seen when you go to the space, there's no air, there's no kind of friction, right? If you see those videos recorded in the universe, in the space, when you grab a ball, when you throw the ball, even though you give a very small punch to the ball, they go bounce and keep on bounce. Meaning that those oscillation, this is a little bit different, but those oscillation lasted for a long time. So what's the difference when you see those throwing the ball here, throwing the ball in space? The friction, the resistivity. So if you decrease the resistivity consuming our energy, then the oscillation will be long. So to decrease the oscillation, we have to increase our resistivity. So we have to consume the energy fast. That's one of the ways you can do it. But when you increase the resistivity, what happens? If you remember those tau, they're depending on R and C, right? So if you increase the resistivity, you have to wait a longer time to go to the value you have. Let's skip this one, does not matter about this. So let's go to page 16 and talk about the frequency domain, what we discussed, and time domain. Actually, these two are not about the different signal. They're talking about the same system, same signal. First one over here, they're talking about the frequency component. The meaning is, this is our system. This is our filter we want to utilize. But previously, if you talk about low-pass filter, they go sharply and go to zero afterward. That's what is ideal case. In real case, they are not flat at low frequency. They need slope to go to zero, and not actually zero. They're slightly waving in zero position. That's the that's the reality we are talking about. So in here, we define several things. We define the frequency response into three cases. First, the band, the frequency we want to pass. The frequency we do not want to pass, and between them. So we divide. First, pass band, the band we want to pass. 12시까지죠? 시간. We want to pass. Ideally, they should be 1. That's the one we want to have. But actually, they are waving a little bit. So we say this the maximum of those things. Those oscillating motion often called ripple. Ripple. Take a look at dictionary, ripple often refers to those oscillatory motion. So say, what is the maximum displacement? What is maximum displacement from 1? Those delta 1 is given as pass band, the band you want to pass. Ripple in pass band, that's what we define. Likewise, in stop band, the band we do not want to pass, we want to stop. In stop band, they are not zero, they are oscillating a little bit. Those oscillation is called stop band ripple, likewise. And ideally, they should stop like this, but actually there's a slope between them. The frequency over here, the frequency that they are smaller than 1 minus ripple at pass band is defined as pass band H frequency, H of pass band. Likewise, 0 plus delta 2, which is 0 plus stop band ripple, when they first touch it, then we call them as stop band H frequency. So we will define them like that. If there's a step input to this system in the box over there. There's step input applied to this box. Output of this box is this, right? Which is ideally they should not have any delay and go like that. That's the ideal case. However, as I explained, they first do the overshoot and oscillate for a certain time. So, first of all, I think you're familiar with that, rise time. The time we typically define in case of circuit from 10% to 90%. They just starting from 10% of the saturation value, the value they will be saturated in a steady state, from 0 to from 10% to 90% of them, the time we pass them will define as rise time in circuit. But rise time means they starting from here, go to certain value. In here, they ideally define that they first hit the settle down point. They define as rise time, the time we want to rise. And then we define overshoot, which is the value higher than the desired value. That's called overshoot. And then they begin to ringing, and we define a certain gap, delta, the ideal value plus delta, ideal value minus delta. And when those ringing become, of course the ringing is not continuously the same. If there's a damping, then there will be slowly goes down until they go to settle down point. So if they are smaller than our defined value, first time they hit those values we call as settling time. And then finally, interestingly, many systems, all the system has their own resonant frequency. Circuit, mechanical system, even chemical system has their own resonant frequency. So when you give a hit, you probably remember that anybody has a brother or sister at home happen to be? Okay, that's good. So take a look at a string, take a look at those one string and tightly put them together and give a pulse. Just give a pulse. What will you have as, what kind of shape of those strings? They are pretty tight. You tight it and give us just a pulse, give a step function. And then what do you expect to see? The easiest thing you can make is like this. They go up, go down, go up, go down. If you give a pulse much faster like this, then they sometimes have like this. But actually when you see that, they will be like this, sometimes like this, and sometimes like this. This one corresponding to our Fourier series, because this is the period of this one is until here. Say this is half of the length over here. This one's period is 2 times length. This one's period is length. This one's period is 2/3 times length. So there will be multiple, or kind of multiple of fundamental frequency. That is what they see it. So this one is fundamental frequency, they say, and typically depending on the resonance. Every system has a resonance. What you can see from the resonance is when you have a wine glass and somebody give a voice, they break the wine glass. Why they are breaking? Well, you already know the answer, because of the resonance, 공진. Resonance is the Korean name of resonance is the 공진. They say, I cannot say it. Typically, they make a high frequency noise. Okay. Tone is high, right? High frequency noise. What that means here is every mechanical structure has their own frequency that they, when input is given at the frequency, they vibrate largely. That's what they say. So every system has their own resonant frequency. Some system, many of the system has multiple of it. Not only one, but also many resonance frequency. And typically, when you give an impulse, those resonant frequency is activated. So they now oscillating. However, if you see the frequency, some of the frequency is depending on the resonance frequency given by the system already. So if you give a pulse, then they begin to oscillate. However, the frequency is not so random. Of course, it's random. However, most likely they oscillate at the resonant frequency. That's the reason we define a ringing frequency, how the frequency looks like. So in long story short, we talk about the filter, we talk about the steady response at the time. Let's have some example how we can utilize this one. I think this is not a scope of our lecture, but if you take a look at our textbook, they'll give it like that. This is called the frequency domain component. So in previous page, frequency and time, they are corresponding like that. In frequency, this is frequency. The black dotted line is so-called ecliptic filter, a type of filter having equation like that. Butterworth filter, which is shown as dot over here, they have equation like that. You can see the equation is different. There are different type of filter. Ecliptic filter, compare those things. Let's talk about the passband. Ecliptic filter is waving, not flat. That means your output, if the input has same amplitude, the frequency or input is happen to be this frequency, they multiply 1. If input is happen to be this frequency, they multiply 0.95 over here. So this system scales, system changes, the input signal come as an output. That's what this one shows. Compared to that, those Butterworth filter, they're pretty flat. So in low frequency wise, the passband wise, this may be better than this. How about here? Stop band. Stop band wise, likewise, ecliptic filter, they are bouncing inside, so they are bouncing over here. So this is the band we do not want to pass. Even though we do not want to pass, then there will be, if the signal happen to be this frequency, about 0.03, 3% of it pass. In here, some of them still pass. They are not 0. So we cannot perfectly stop the signals. In case of Butterworth filter, they are flat. It's almost 0. So in stop band wise, ripple wise, the Butterworth filter is better than ecliptic filter. However, let's take a look at the between the passband and stopband. This one drops sharply. This one drops relatively not so stiff, smoothly. This one, passing and stopping, is relatively well separated. This dot, which is this one pass, this one pass, this one pass, this one pass, until this point. Stop and pass does not well separated. So, what you can see from here, in real filter, it's almost impossible to make a perfectly selective one. You have to select not only Butterworth filter, ecliptic filter. If you go to the MATLAB, there's different kind of filter is installed inside the MATLAB. You have to select what kind of filter you want to have. If you say, okay, I really want to separate pass and stop, that's really important for you, you have to select the filter. In design, tweak these variables to be best match to use this one. That's how we do it. If you say, I really do not want to pass anything in stopband, or scaling in passband is a problem for me, my sensor is very sensitive, then you have to select a Butterworth filter. And how will be their time domain response? As you can imagine, ecliptic filter, Butterworth filter, ecliptic filter is quite sharp, and we cannot perfectly block the stopband. So expect that there will be some high frequency components still exist. So you can see that there are still some high frequency components still exist. They are high in overshoot, they require longer time to settle down. In case of Butterworth filter, as they are a little bit slower, so their rise time is slower than the ecliptic filter, but they settle down faster because they can separate. Because there's 1 and 0. So you have to select. What I'm saying here is two things. First of all, you have to select the right one. Second, you have to also think about time domain signal, because in filter we typically think about in frequency domain, but you have to imagine how their time domain signal looks like, because this is what we are really using it. Okay? So that will be pretty much of it today.